So the 68, 95, 99.7 rule is also called the empirical rule. We use this to draw a picture of the model. Remember, it's a curve that looks like this. That's really a bad one. In the center of this curve is the mean. And then we have 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. And then we have 1 standard deviation below, 2 standard deviation below, and 3 standard deviations below. Okay, that's what our number line is going to look like. Now, within 1 standard deviation of the mean lies about 68% of the data. Okay. Within 2 standard deviations of the mean lies about 95% of the data. And in 3 standard deviations of the mean, about 99.7% of the data. Then we talked about how much is in the tails. Okay, this is how much is in the center. If 68% is in the center, that leaves 32% left in the tails. And there's 2 symmetrical tails because our normal model is bimodal and symmetric. So that means on each side of 1 standard deviation, about 16% of the data is above 1 standard deviation, and 16% of the data is below 1 standard deviation. And it's approximate, it's not exactly 68, there's a decimal point, but you'll just, in general, we can memorize these numbers. If we have 95% in the middle, 100 minus 95 is 5. And in 2 symmetrical tails, that's 2.5%. So above 2 standard deviations is 2.5% of the data. That means 2.5% of the time something is more than 2 standard deviations from the mean, which is pretty unlikely. Okay, it's unusual. That's a small percentage. And to be more than 3 standard deviations from the mean, 100 minus 99.7 is 0.3. Divide that into 2 equal tails, and we get about 0.15%. So data is only 3 standard deviations, more than 3 standard deviations from the mean, about 0.15% of the time. Right? So these percentages can be used to answer the questions on number 25 and 26 when it's saying, in what interval would you expect the middle 95% to be? Okay. Let's put some actual numbers on this. We're going to sketch a normal model using the 68, 95, 99.7 rule. I left off a 0.7 on there. Given the birth weight of babies. The birth weight of babies are normally distributed. This is the shape, normal. This is the center, a mean of 7.6, and the spread, a standard deviation of 1.3. Okay. When it's given in that n parentheses, it's giving you shape, center, and spread. Because it's normal, there are no outliers. The normal distribution has no outliers because it's unimodal and symmetric. So we're going to draw our curve. And in the middle goes the mean. In this case, our mean is what? 7.6. And then the next is plus 1 standard deviation. So 1 standard deviation would be how much? 7.6 plus 1.3 is 8.9. And then we add a 1 standard deviation again. 8.9 plus 1.3 is 10.2. And then 1 more standard deviation, 11.5. That's what our normal model looks like in the context. The last slide was just a general normal model. And now we're going to go backwards. Yes. Are you asking a question or explaining something? Okay. Now I'm going to go backwards. I'm going to subtract 1 standard deviation. What value is that?
6.3, 5, 3.7,
6.3.
Okay.
5.
6.3 minus 1.3 is 5. And 6.3 minus 1.3 is 3.7. Okay. So it's going to say draw the model, clearly label it. So clearly labeling it includes saying that this is 68%. And this is 99.7%. Now when it asks us to describe the normal model, we're going to say approximately 68% of babies born weigh between, what are my two values for 68%? 6.3 pounds and 8.9 pounds. Okay. I'm going to add something to your homework tonight. Find out from your mom, your dad probably won't know, how much you weighed when you were born. Your dad might.
My dad wasn't there.
So, I mean, it's probably about 50-50. I think my husband remembers what my oldest weighs, but probably not the youngest. I don't know. Anyways, find out how much you weighed when you were born. Okay? The birth weight of babies is data that is tracked, right? Every baby gets born and recorded. So we have the data for the entire population of babies that are born in a hospital at least. Okay? So we know the mean and the standard deviation of this because we keep track. Okay? So we'll find out, where were you? Where did you lie on this normal model? Okay? Now, so approximately 68% of the babies born weighed between 6.3 and 8.9 pounds. Approximately 95% of babies born weigh between 5 and 10.2 pounds. And then approximately 99.7% of babies weigh between 3.7 and 11.5 pounds. So if your mom tells you you weighed 12 pounds at birth, that is a big baby. And that would be considered very unusual because that is more than 3 standard deviations from the mean. We know that happens only about 0.15% of the time, right? And if your mom tells you you weighed 3.5 pounds at birth, you were probably a preemie. And that's unusual as well. That's only about 0.15% of the time. My oldest daughter was 5 pounds at birth. Right there on the 2 standard deviations mark. Right? It still hurt, don't matter. So, I just can't imagine a 12-pound baby. I mean, hey, so draw this one. In your notes, I want you to draw this. ACT scores, the ACT scores at a certain college. Data we have, right? The college keeps track track of every student's incoming information, their GPA, their SAT score, their ACT score. They are normally distributed with a mean of 21.1 and a standard deviation of 4.4. Draw that normal model, label the axis. All right, so our middle is 21.1. Adding one standard deviation, which is 4.4, puts that at 25.5, right? Adding another standard deviation, 4.4 to that is 29.9. And adding one more standard deviation to that is 34.3. And then subtracting, that's the one I hate doing. 21.1 minus 4.4, 16.7. There's no shame in using a calculator in this class. And 12.3. And 7.9. Okay. Now, again, we have our 68% within 16.7 and 25.5, 16% of the time. 95% of the time, the ACT score is between a 12.3 and a 29.9. And 99.7% of the time, it's between 7.9 and 34.3. So I want to talk about a few of the questions you're going to have on tonight's homework. Can you describe the worst 2.5% of scores? Where are the worst 25% of scores? What score is that below? 2.5%, sorry. Right? Wouldn't that be less than 2 standard deviations from the mean? That's 2.5%, we said, because 95, right? 95% is in the middle. That leaves 2.5% in each tail. So the worst 2.5% of scores is less than 12.3. The middle 68% of scores would be between 16.7 and 25.5, right? What would you consider? What score would you consider unusually high? Right? Okay, so most of you are saying 34.3 is definitely unusually high, but isn't 2 standard deviations still only 2.5% of the time? So couldn't you argue that scores above a 29.9 are also pretty unusual if they only happen 2.5% of the time? Okay, so when you're asked about what scores you believe are unusual, you really want to talk about 2 standard deviations or more from the mean. Okay, you're not marked off if you say, I believe it needs to be 3 standard deviations from the mean to be considered unusual. That is true. But we can make an argument for 2 standard deviations being unusual, and that's going to be our standard. 2 standard deviations from the mean is going to be our standard for unusual. Okay, so 29.9, 2 standard deviations from the mean. Okay, so greater than or equal to 29.9 would be considered unusually high. What percent of people have a score above 25.5? What percent have a score above 25.5? Is it 32? 16, right? We have 68% here in the middle, which leaves 38% in the tails. So 16% about are expected to have a score above 25.5. So approximately 16%. That's all you're required to do in the problems tonight. Draw the normal model and then answer the questions based on this and then what we had on the last slide, those percentages that are left in the tails.